Eric Burgess here. The average person watches 25 DVDs per year. A random sample of 45 people reported that the average number of DVDs watched per year was 22.44. The population standard deviation is 9.6 at the 0.05 level of significance. Can it be concluded that this represents a difference from the national average? All right, so our first step here is let's write out our null and alternative hypothesis. So H0 and HA, the alternative. So null hypothesis always starts with that something is equal to something else. In this case, we are dealing with an average. And the null hypothesis, right, is just what the average is claimed to be, what it equals. So the very beginning usually has this. The average person watches 25.5 DVDs per year. This isn't tied to a sample. This isn't tied to some study. They're just basically stating that this is the reported case for everyone. So it's going to be that the mean is equal to 25.5. All right. And then the alternative is going to be tied up in what they're trying to say. So right here at the end is typically where you want to look. We see it says, can it be concluded, all right, that this represents a difference? So the key word here is difference. That just means it's not 25.5. It could be above or below 25.5, which would mean that this is a not equals to sign. So the mean is not 25.5. So this is going to be our two hypotheses. Now, I like to go ahead and go through and take out all the stuff that is in this question, get the numbers out of all these words. So we've got a couple things here. I'll go ahead, I'll do this in green. So we've got at the beginning our mean, mu, that's equal to 25.5. And this is the population mean. Then we're told that we have a random sample. All right, random samples are represented by the variable n. And we're told that we have 45 of those. And reported that the average number of DVDs was 22.44. So this average number of DVDs goes with the sample. So this is a sample mean, where this one didn't have a sample, so it was a population mean. This one's a sample mean, so that's going to be x bar, and this is 22.44. And then we're told the population standard deviation, that's sigma, and that is 9.6. Now, because we have a sigma, this also tells us that we're going to be using a z-score, because when we know the population standard deviation, we can use a z-score. At the 0.05 level of significance, so that is our alpha, level of significance 0.05. And then that goes on to tell us what the alternative hypothesis is. So we've got the numbers out of here. Now it's time that we can go two ways. We could draw a chart, or we could draw, or a graph, I mean to say, or we could get a test stat. Let's go for the test stat first, because it'll make it so that when we draw the graph, everything will be done at the same time when it comes to the picture. So because we're using a z-test, we know that we need a formula. The formula for a z-test, if you don't know, you could always go look it up if you can't remember. But we're dealing in a difference of means. And so we're going to use the difference of means 1, which is the sample mean minus the population mean divided by, and then normally, right, it's just by sigma. But since they're means, they have a sample size, n. And so that's what we're going to use here. We're going to go ahead and divide out by n. So we can just plug in our numbers. And now this right here is our test stat, right? The reason it's our test stat is because it came from our study. We're using, if I were to highlight them here, maybe in green, this comes from our study, and n has to do with our study. So we're comparing values that we get from our study to values that we know about the population, like the population mean and the population standard deviation. And so we're doing a comparison to them, and this is going to give us a test stat that we can compare meaningfully to it, so that when we can make some conclusion about these hypotheses here. So okay, x bar, we're told that that's 22.44. The mean is 25.5. And then we go ahead, we divide by sigma, which is 9.6. And we have a radical n, which is 45. Plug this into your calculator. Now there's another way to do this. So if your professor uses the calculator method that doesn't involve the formula, I'll show you how to do that too. Only takes a split second. It's a good way to check your work. So we're going to type this in. If you hit the green key and then y equals, you can type a fraction. So I'm going to do that. 22.44 minus 25.5. And then we want to type the fraction first. Typically, it makes inputting stuff easier. So we're going to hit the green key, y equals. And this is going to give us a fraction, 9.6. And then we're going to do the square root of 45. If we hit enter, we get out our number. So this is our test stat. We get out negative 2.13. I'm going to round to 2 places. So negative 2.14. Now, if you want to check this, or if you use the calculator method, you just need to go to the z-test. So we're going to go to stat, calculation, or tests, we want to go to tests. And then it's the very first one, z-test. So we're going to do that. We have statistics, which means that we have these numbers over here. If we were given data, we'd have to compute this stuff, which the calculator can do for us, which is really nice. So our mu naught is the population mean, this mu, and it's 25.5. Our sigma is 9.6. Our x bar is 22.44, sample mean. N is 45. And we're saying that mu, which now they're talking about this mu. So mu naught is the population mean, where we're comparing our mean. We're saying that it's different, that this mean is different than the population mean. So we want it on this one. This also means that this is a two-tailed test. So maybe we should write that in too. This not equals to means two-tail. It's going to be important. So we're going to do that. And now I'm going to go ahead and hit calculate. And we get out our values here. So we get a z. And we see we get the exact same z-scores. So that's good. This also gives us the p-value. So you could find this from the chart. But we're just going to take it from the calculator here. I'll show you how to get it from the chart too. 0.032. And that is really all we care about here. So we've got our z-score, our test stat, and our p-value. You could use this in the calculator to check your work, or you could just get it directly and skip this step. Totally up to you. So from here, we want to go ahead and plot some stuff and compare it. So what we're going to do is make a chart. And I'm going to do it down here. Just draw in a normal distribution. You know, something like this. Good enough. In the middle is 0 because it's a z-score. And keep in mind, this is a standard normal distribution. So we know that for standard normal distributions, they plot z-scores. And z-scores in standard normal distributions will always have a mean of 0. Right, the center is the mean, which is 0, and they'll have a standard deviation of 1. So we can just plot over negative 2.4 to plot our test stat. Now, we also need to find our critical value before we go any further. So there's going to be, since it's a two-tail test, that means this tail and this tail are going to be shaded, and there's going to be some critical value that goes with these things, right? We know that the distribution is symmetric, so if we find the lower one, that's fine. And the area that the total area this is given to us through our level of significance. So we know that the total area altogether has to be 5% or 0.05. So if we were to take 5% or 0.05 and divide it in half, right, because half is over here and half is over here, we get out the area that these are. So the area this thing takes up is 0.025, and the area this part takes up is 0.025. So given an area, we can find a z-score. Now there's two ways to do this. One's the chart, the other is the calculator. let's go ahead and use the calculator way first. So this is a standard normal distribution. So we're going to go ahead and go to the distribution menu on the calculator. So we're going to hit second distribution, and then we're going to go to inverse normal, right? Because normally we're going to go from a z-score to an area, but we're going backwards. We're doing the inverse. So we're going to do inverse normal to go from an area to a z-score. So that's number 3. The area is this lower one. Now this is a symmetric curve. So if we find this lower value, it'll be the negative version. And we can just take the positive version for this part because it's symmetric. So the negatives on this side, positives on this side. They're the same distance from 0, just in opposite directions. So we're going to put in this lower value, 0.025. And then we're going to use symmetry to get this other value, like I just said. It's just the positive version. Now, really important, your mean is 0, standard deviation is 1, because we're using a standard normal distribution. Very common mistake to put in the sample stuff up here. You don't want to do that if you're using a standard normal curve with z-scores. So the z-scores, these are going to be your mean and standard deviation. We're going to hit paste, hit enter, and we get out our critical value. So on the negative side, we have negative 1.96, and we could go to the positive side, 1.96. Remember, because it's symmetric. Now, if you are required to use the chart, you would look up 0.025 as an area in the chart. So let's go ahead and go to the chart. I have one right here. We're going to look for 0.025. So we've got, and it's an area, remember? So I also see very commonly people looking at the z-scores. See how these are labeled z? We don't know z. We're trying to find it. So we're going to look in the areas, right? Because these scores give us areas. So we're just going to go backwards. So we're going to look for 0.02. There's 0.021. It might not be exactly on here, but we just want something that's very close. Here's 0.0255. Oh, here we go. Exactly right there. That's beautiful. So this is 0.025. I was looking at the screen and not my iPad, so I want to highlight it though for you. Whatever. It's right here. Look at where my mouse is at. 0.025. And if we look at how this connects to z, it's negative 1.9, and then we go up 6. So negative 1.96, which look at that. That's exactly what we got right here. So if you're using the chart, that's how you would do it. And again, you can use symmetry. So once you have the negative one, you just flip it and make it positive, and this will give you the positive side. So we've got our critical values. Now we can plot our test value a little easier. It's much easier to tell after you've done the shaded regions. So this is negative 2.14. So we're going to go ahead and plot that. And that's going to be somewhere over here, right? Negative 2.14 is our test stat. And so we see that we're in the shaded region. Because we're in the shaded region, we say that we reject the null hypothesis, right? Because if the null hypothesis were correct, we would be at 0 or close to 0. This whole unshaded region is basically the region that if it is different, it's by chance. It's just our sample when we did our study. It just so happened to be, maybe we just didn't get enough people. But because we're so far away from the middle here, we say, this is probably not by chance. So we say this is probably wrong. The null hypothesis is probably wrong. So we say reject the null hypothesis, HO. And then we need to look at our claim. Now that's something I didn't identify right at the beginning. Typically you want to do that. So with the claim, we look at this and we say, well, can it be concluded that this represents a difference? So this means that the one that's a difference is the claim. So that means that's HA, right? Because that's the one that says it's different. This is our claim. So we reject H naught. We don't think it's true, which means that we think the alternative hypothesis has merit. We think it's true. And so we've done a study and we've produced evidence. So we say there's evidence to support the alternative hypothesis. That's what you would write. There is evidence to support the alternative hypothesis HA. And some teachers want you to be more specific. So you may need to include to support the alternative hypothesis that there is a difference in the average number of DVDs watched from the national average. Like you would be more specific and tie in to specifically what you're concluding, because this doesn't really tell anyone if they were reading your report, what your conclusion really was. They'd have to go and look and reread the problem. So it's kind of good manners to be a little more specific here, but I'm going to leave it at this because this is the really important decision stuff. I'll let you get more specific with how you write everything out. Let's cover the p-value decision-making process. Then I'll show you how to get the p-value using the chart as well. So this p-value expresses the area to the left of negative 2.14, but it's actually doubled. And it's doubled because it was split in half, right? There was half down here and half up here. And so remember, the rule is that if the p-value is less than alpha, then we say we reject the null, because it means it's in the shaded region. It's smaller than the shaded region. If this is bigger, the shaded region is bigger than this. So it would have to be in there, which we can see clearly because our test stat is in the shaded region. So this makes a lot of sense. But this is the entire p-value instead of it being split in half. So if we wanted to compare this p-value to this alpha, we would have to split this in half. Or you could compare it to before we split it up. So before we split alpha up, it was 0.05. And this is clearly bigger than this. So we would say that we would reject the null hypothesis. And then we would make the same conclusion that we have evidence to support the alternative. So that's the exact same conclusion using the p-value. So if we wanted to find this using the chart, we need to find the area to the left of this guy. So down here, we'd find the area to the left, and we would double it if we want to compare it to this alpha. If we want to compare it to this alpha, we would not double it. So when you're using the chart, typically I'll just, compare it to this thing. But I'll show you that they'll end up being equivalent. So we're going to go to the z-score table and look up negative 2.14. So go to the z-score table. Here's negative 2, and then here's 0.04. So the z-score we are interested in is this one. Oh, we want negative 2.14. 2.1's right here. So negative 2.14. So this is the z-score right here. I'll circle it in black or something as well. So 0.01618. So let's go write that down before I forget it. 0.01618. 0.01618. This is the area to the left of this up here. And if we compare it to this alpha, we'll reach the same conclusion. It's smaller than the alpha. Obviously, it's this area right here. And so it winds up that we would still reject H0. But if you want to compare it to the main alpha, you would need to double it. So we would take this and go 0.01618. Because, right, there's an above portion too, because this is a two-tailed test. So we would double it, and we get 0.03236. And if you round, you see we get the exact same p-value. And we could compare it to the original alpha. So the p-values for a two-tailed test could be a little bit confusing at first, but just keep in mind that, you split it here, and this is the whole alpha before splitting. This is alpha after splitting. So if you use the chart, it's easier to just compare it to the split alpha. But if you're using a calculator, you're going to want to look at the complete alpha up here, or you're going to want to split this in half and then compare it to the split one. Like, it's up to you. It's just a matter of what you prefer to do. But you reach the exact same conclusions, and all that stuff is great. If you have any questions about this, feel free to let me know. Subscribe and hit that bell icon for future videos, and we'll catch you in the next problem.